When we solve a system of equation using matrices and row operations, what we're trying to do is we're trying to get a matrix that looks like this. If we have three variables, this is what the matrix should look like. Ones along the diagonal, zeros elsewhere on the square part of the matrix, and numbers on the other side of the matrix. And if we have the situation where one of the variables is eliminated from the equations completely, or a situation of multiple solutions, that would mean that a whole row is zeros. So that could happen as well. So in order to get a matrix to look like this, we can do row operations. And some examples of allowable row operations are to switch rows, to multiply a row by a constant, or to replace a row with a sum of the row and another row. We can also replace it with the sum of a row and a multiple of another row, and combine steps in that way. So our first step is to write the matrix. So using this system, the first equation would be 1, 1, 1 on the left part, and then another 1 on the right, and then 2, negative 1, negative 1 for the second row, and then 11, and 1, 2, negative 1, and 4. So that is our matrix. And now let's label the rows of that matrix. Row 1, row 2, and row 3. And recall that our goal is to make it look like this. Now my method is to go in order and first try to get the first row to look like this and then move on to the second and third row. But if you see an easier way to do it, you can always change the order. So I like to start with row 1. So we're going to first replace row 1 with row 1 plus row 2. If we do that, then row 1 plus row 2 would give 3. 1 plus negative 1 is 0. 1 plus negative 1 is 0. And 1 plus 11 is 12. So we only do that to the first row, and then row 2 and row 3 we leave exactly how they were. So 2, negative 1, negative 1, 11 was row 2. 1, 2, negative 1, 4 is row 3. So one other thing that we can do is if it seems easier to switch something back to an equation and do something in an equation, we can always do that. So looking at this first row now, y and z are the second two columns, and those are eliminated from this row. So we could turn this into the equation. Remember, this is the x column. 3x equals 12. Divide by 3, and we get x equals 4. So we can replace this first row now with 1 for the x, and then 0, 0 for the y and z still, and then replace the 12 with a 4. In row operations, this would have been multiplying row 1 by 1/3, or dividing by 3, as we did in this equation. Okay, and that would give 1, 0, 0, 4. So sometimes you might want to stay in the matrix and work with rows. Other times you might want to use an equation like this in order to simplify a row. But using that equation would be the same as using a row operation in some way. It's just writing it a little bit differently. So I'm just rewriting the second two rows exactly as they were. And now if you look, we have the first row in the correct form. So the first row is done. And now we want to move on to the second row and the third row. So starting with the second row, this is step 3. we're going to replace row 2. Whenever we refer to row 1, row 2, or row 3, we're always referring to the matrix right before. So this is row 1, this is row 2, this is row 3. We're going to take row 2 and we're going to subtract 2 row 1s. So we're going to subtract 2 times row 1. Okay, so the first entry would be 2 minus 2 times 1, so 0. Negative 1 minus 2 times 0 is negative 1. Negative 1 minus 2 times 0 is negative 1. And 11 minus 2 times 4 is 11 minus 8, which is 3. So we replace the second row with that, and then rewrite the first row and the third row. Okay, and now, even though we're not quite done with row 2, what we just did is we eliminated the x column from row 2. Let's do the same and eliminate the x column from row 3. So this is row 1, row 2, row 3. Our fourth step will be to take row 3 and replace it with row 3 minus row 1. Okay, that would be 1 minus 1, which is 0, 2 minus 0, which is 2, negative 1 minus 0, which is negative 1, 4 minus 4, which is 0, and then rewrite the other 2 rows. Okay, so now we have x eliminated from the last 2 rows, which makes our job a little bit easier. Okay, next, let's go back to row 2 and try to fix row 2 some more. So remember, in row 2 we're trying to get 0, 1, 0. So row 2, we want to do something about this entry. So we could do row 2 minus row 3. So row 2 minus row 3 means 0 minus 0, negative 1 minus 2, negative 1 minus negative 1 is 0, and then 3 minus 0 is 3. One, 0, 0, 4 is the first row still, 0, 2, negative 1, 0. And you can see, I haven't been writing the augment line. You can see that the middle row is almost how we want it. We just have a negative 3 in the spot where we want a 1. So let's take that and write it as an equation, knowing that we're in the y column here. So we solve the equation, negative 3y equals 3. Divide by negative 3 to get that y is equal to negative 1. So now we can put a 1 in that row, 0, 1, and 0, and replace the 3 with the new answer, negative 1. So that sixth step used an equation in order to get 1y instead of negative 3y. Because having 1y is the same as having a 1 in that correct spot in the matrix. And you can see we're getting a lot closer. Now the second row is in the correct form, and all that remains is to fix the final row. Now to get this last row how we want it, we want to turn this 2 into a 0. One way we can do that is by taking row 3 and replacing it with row 3 minus 2 times row 2. Okay, that would look like 0 minus 2 times 0. 2 minus 2 times 1 is 2 minus 2, which is 0. Negative 1 minus 2 times 0 is negative 1. 0 minus 2 times negative 1 is negative 2. I'm sorry, positive 2. Because we're multiplying the row 2 by a negative 2. Okay, keep the other two rows the same. And now we almost have what we want. The x and y spots are empty and we just have the z slot. So we have negative 1z equals 2. Divide by negative 1 and we get z equals negative 2. So 1z equals negative 2, which means that if we were to rewrite this again, 0, 0, 1, negative 2 would be the last row. So this is now our solved augmented matrix. 1, 0, 0, 4, 0, 1, 0, negative 1, 0, 0, 1, negative 2. And what this means is that the x value is 4, the y value is negative 1, and the z value is negative 2. So as a coordinate point, the solution to this system is 4, negative 1, negative 2.